I'm Jim Anderton, and this is the Industry Insights and Trends podcast. On this show, we'll explore the length and breadth of 21st century engineering, from civil engineering mega projects to innovation at the quantum level. We speak with subject matter experts and industry watchers from every sector of the engineering discipline.
You know, in medicine, engineering is not just important, it's more important now than ever. Medical technology, it's moved from an engineering standpoint from devices that assist physicians and surgeons for doing their job to devices which are actually implanted inside the body, doing all kinds of interesting things such as fracture fixation or drug delivery. I'm joined by Jim Hammerand. He's managing editor of medical design and outsourcing. And Jim is an expert in medical devices in the engineering world. Jim, welcome.
Hey, Jim, thanks for having me. I appreciate it. And you'll love this. My father's a Jim and my son, well, he's a James, because it'd be weird to call a 3-year-old Jim, but one day he may also be a Jim.
Yeah, we'll just confuse the hell out of the audience with this. It'll be all Jims. It'll be the Jim channel for the remainder of this conversation. That's just fine. Jim, it's, medical devices from an engineering standpoint. We see, if we walk into a hospital or doctor's office, we see machines and gadgets, all over the place there. And there's a tendency to think of these things primarily as assistive devices. So it's an EKG machine, or it's maybe a heart-lung machine. It's the kind of technical devices that we see that support the process of medicine. But there's a lot going on that's in vivo as well, isn't there?
Yeah, absolutely. Absolutely. I mean, and it has come so far from years in past where we've got implants that are getting smarter. We've got catheters that are getting smaller and able to do more things inside the body to treat people in ways that we call minimally invasive, where, for example, previously you'd have to crack open someone's chest to replace a heart valve. And now you can go in and do that with a catheter delivered through their veins and have a faster recovery, fewer complications, and ultimately better outcomes. So it's really, really exciting time in medtech right now.
Yeah. Now it's that's certainly something we're all familiar with. Now you can do things with a scope now that were never imagined possible. And we originally thought of this as something you sort of clean out cartilage in a knee. And now I understand, gallbladder surgery is routinely done this way. We're talking about heart valves. Has this revolution been caused by a change in how small the devices are, how accurately you can move them, the materials they're made of? How come suddenly that there's a sort of a blossoming of this sort of remote surgical technique?
So many different trends. I mean, everything from the design process being more computer assisted, where you can now use computers to simulate device design, to test them, and to quickly then turn to 3D printing to not only develop quick turn prototypes of your devices, but to build models of patients and their different anatomies. If you want to build a model of the heart or the lungs and see how well that catheter can take all the twists and turns without kinking or without puncturing part of the anatomy. So a lot of it is on the design side. We've got, some new metals. A lot of med tech is still old fashioned, where, for example, in heart valves, we're still using animal tissue. And a lot of these heart valves are actually sewn by hand, thousands of stitches over dozens of hours. But there's a lot of more advanced manufacturing techniques coming online for better quality, better scalability. Again, I mentioned 3D printing, but really the idea that you can much more efficiently and effectively make devices today is a huge leap forward. And with the kinds of materials, advanced materials, one that I'm particularly excited about is material your audience may be familiar with, nitinol. I've got kind of a reputation among our life science group in the medtech industry now as a bit of a nitinol enthusiast. And I'm not an engineer. I'm not a doctor. I just, my first experience with nitinol was those eyeglasses where you could bend them and twist them and they'd never snap and they'd always return back to their shape. And perhaps when I had braces as a younger guy, I had the orthodontic guide wire on there, the arch wire. But now nitinol is really taking off in a new way. And I think it's the hottest material in medtech. And it's certainly what I'm most excited by because it's the kind of thing that engineers can actually get their hands on, influence at all stages of the manufacturing process. But also there's so many ways that it can go wrong. And that's kind of what's special about medtech is it's so heavily regulated. And you got to keep things simple because there's so many ways that a device can, cause a catastrophic failure. And that's a problem when it's inside a patient.
Yeah. Now, just for the non-mechanical engineers out there, nitinol is a part of a class of materials called a shape memory alloy, and it's something which actually can retain its shape as formed and restore its shape to its original form with the application of energy, usually heat, after it's been deformed, and that's had for engineering applications and things like thermostatically controlled valves, sort of mechanical devices for the process industry. But we're talking about something where these are devices that are implanted inside the body. How about biocompatibility? Is that an issue?
It is an issue. You've got to be careful with the coding because, of course, anytime that they are investigating a new device that uses nitinol, they're always trying to exclude patients that have nickel allergy. But you are able to, as long as you are coding or finishing these devices appropriately, you can prevent the leaching from the nickel leaching that can be a problem. And we've been doing this for a while, so it's pretty good. And then there are other devices where it's not necessarily an implant, but let's say for treating atrial fibrillation, that's a huge problem for patients. And what they're able to do now is using a minimally invasive catheter, they can create a device that goes inside of your heart, comes out of this tiny little tube, and expands into the shape of, say, a beach ball or sometimes a flower, different shapes within the heart to apply electricity through different modes. Pulse field ablation is the one that's really taking off right now, right, where it's generating electric field, electroporating these heart cells. And the idea is with atrial fibrillation, you've got these erratic heart signals that are saying that they're beating off pace or they're beating too much. And so what you can do is you can go in there and you actually scar the heart tissue to block those erratic heart signals from getting through. And you can do this with thermal energy. You can do it with extreme cold, and kill the heart tissues. Now they're electroporating to avoid damage to nearby nerves. And the way they do this is this catheter comes inside your heart and it expands to create, in some cases, a global electrode to zap the heart, withdraw. And this is a same day procedure. People go home and it's really, really cutting edge. Would not be in this case possible without nitinol because its ability to collapse down but then return to its shape.
That's incredible innovation. You think of it when I think of things that collapse down and have to be shaped. You think, of course, the traditional is the stent. In vascular surgery, where basically you're going to take a deformable alloy, coil, and inflate it with a balloon, sort of, prop up that blood vessel there, then withdraw the catheter. And then, you might heparin coat it or whatever you've got to do to prevent it from throwing clots. But with shape memory alloys, in this case, it sounds like the patient's own body heat kind of causes this thing to expand like an umbrella.
And it's more the pseudo or the super elasticity where when it's compressed down into that catheter, the whole time it wants to expand by itself. It wants to pop back even independent of temperature. And so as soon as it is released from that catheter sheath, it pops into its shape. Say in the case of a heart valve, they can compress these down, a replacement heart valve, go into your heart, and it expands in there. And they'll anchor it, or sometimes they have to retrieve it and they can collapse these things back down for removal. So it's really that super elasticity that's so helpful. For the stents example, that's good radial force can push to keep the vessel open. For a heart valve, that force can anchor it within the bad heart valve, so it stays where it needs to. Or with that self-expanding catheter. Another example of a self-expanding catheter that's really exciting is one used for renal denervation. So this is for patients who have had a hard time for a long time managing high blood pressure, their hypertension with blood medicine. What they can do is now this just got approved recently. They can take this tiny little catheter. It goes into the arteries that feed your kidneys, and it zaps the nerves, and that can actually have long-lasting effects to lower your blood pressure. It's a minimally invasive procedure. They're in, they're out. And hypertension, it's one of, if not the biggest killers globally. And again, it's all thanks to this little metal that can expand to a spring. And what they like about that now is they're trying to say, hey, what if we go in and we zap other arteries to other organs? So right now they're trying to combine kidney denervation with liver denervation, see if they can get better outcomes. And they really don't need to modify the device at all because it's self-expanding, so it can expand to accommodate a larger vessel. And that's another thing that's really important with med tech is you've always got exclusions. You've got, you can make a device, you can standardize it, you can test it, but sometimes a patient's anatomy, maybe their vessel is larger than average or smaller than average, and that device won't fit. But what's nice about nitinol is a lot of times it can expand to accommodate an even wider variety of patient anatomies. And that's just another reason why it's just so exciting.
No, that's, I mean, it's remarkable engineering story. From a patient perspective, it's what sort of what is the impact there? Because I mean, we think of things like a heart valve. I'm thinking, 2 weeks, maybe 3 weeks in a hospital. And you're talking now about some procedures here where it's a day or two and you walk out into your own steam.
Yeah, and that's the goal. I mean, minimally invasive med tech is another big passion of mine, which I think is why I'm so interested in nitinol, is because it enables it so much. But a good example is robotic surgery, right? Instead of laparoscopic or open surgery, if you can go through tiny keyholes, minimize the size of your wound, you can heal faster. You have the potential for fewer complications, and a lot of times a faster, simpler, and easier to repeat procedure. Because you have to remember, in healthcare, one of the biggest stresses right now is the shortage of doctors, shortage of nurses, shortage of OR care teams. So anything we can do to make it easier on them so they can be more efficient, not only in a day, but you look at orthopedic surgeons. I mean, these a lot of times these are bone carpenters. They're really working hard. If we can, take some of the work off them, some of the stress off them, not only on a day-to-day basis with something like surgical robotics, but also lengthen their professional career, then that's really helpful for our entire system, and that's ultimately good for patients.
Yeah, Jim, you touched on a couple of issues there. One, of course, is a shortage of skilled people, and of course, the other is the you touched on this automation factor. What about robotics? I mean, we've been hearing about how we expect that robotics are going to take over a lot of functions in medicine and in surgery, and there are surgical robots out there now. But could you combine, do you think, in the future, robotics with this sort of microscopic, laparoscopic, catheter based surgery?
Oh, of course, it's already happening. The world's largest surgical robotics developer, Intuitive, they've been at it for, I think, 20 years now. And they have really dominated the space with essentially laparoscopic procedures performed with robotic assistance. Now, there's still a surgeon at the console. And what's interesting about them, they started, they like to say they aimed for the heart and landed in the gut. They originally tried to do cardiac procedures like these, but where it really took off was abdominal and procedures like prostatectomies, where you can go in and minimize the complications, minimize procedure time, improve the outcome. So robotics is really, really gaining traction right now in med tech. One of the most exciting startups I'm covering right now is a company called Capstan Medical. They've got these collapsible nitinol heart valves, but they've also developed, and they're already testing in humans, a robotic system to aid in the placement. So that helps them, again, standardize procedure, helps them give them better control of where exactly in the heart the replacement valve is landing, to minimize where they have to move it around a little bit, and for ultimate outcomes. And there's all sorts of different ways that robotics, even outside of surgery, are starting to be used in med tech. And it just, again, a very, very exciting time. And when you see the combination of advanced materials with robotics, layer on AI to help doctors, make decisions during procedures, or to help them plan procedures, or to help them go back and review how a procedure went, almost like looking at, game tape after a football game. It's really encouraging about where the industry's headed.
Jim, robotic or human surgeon, how do they see where they're going?
Well, there's a whole bunch of different ways. Sometimes they have cameras on the inside. A lot of times, if you're doing something without a clear line of sight, they'll have imaging. You'll be performing a procedure under fluoroscopy. But a lot of what is enabling robotic surgeries right now is smaller cameras with better visibility. And of course, when you're in the body, you've got to have all sorts of ways to keep that camera clean, almost like the cameras on the NASCAR race cars, where you see a wiper going on them or a film coming off them. So they're irrigating them, they're flushing them. That's one of the challenges, is getting up close to see what you're doing. But that is, has already, I think, been well paved by all sorts of scopes in the industry to see within the body with a minimal footprint where you can't actually get a good eyeball on.
Yeah, yeah. Now there's no way you can do a podcast, a video, an article. There's nothing you can do in our fields, our engineering related fields, without bringing this up, and that's AI. Essentially, what conversations are you hearing in the medical device industry? Are they talking about it? Are they thinking about it? Are we looking at applications?
Oh, absolutely. And, I think with all the conversation around AI, it's very important to define what we mean by AI. Machine learning right now is very useful in med tech. We've got systems out now that can help when you're getting a colonoscopy, can help the physician. It can actually flag spots on the colonoscopy that look like trouble spots. So the physician performing that colonoscopy can go in and look. It improves. It actually does improve the detection. And if you're going to get a colonoscopy, you probably want to do it early in the day when someone's more attentive versus later in the day when they've been doing it all day and maybe they're going to miss things. So when you have things like that, like imaging, diagnostics, anything where you're looking at a lot of visuals and you can try to figure out what commonalities there are and how you might be able to flag problem spots or aid diagnosis, that is really, really promising right now in med tech. The things I think that outside of med tech, AI like LLMs, large language models, generative AI, I think right now there's a lot of people looking for a problem. They've got a solution. They're looking for a problem to solve. I would say right now in AI, everything is more in machine learning and how you can better enable physicians and doctors to make decisions either for planning procedures, during the procedures, or after the procedures to, for instance, measure how well a patient is recovering, given a large data set of other patients who had a same kind of procedure, and try to predict what kinds of outcomes they might have, and if there's any way to intervene and make them better.
Yeah, yeah, yeah. So we're talking about a story here of better outcomes, less pain, faster recovery time, less discomfort. It's a win-win-win down the line. How about cost? Cost is a major issue in the healthcare system at this point. Can we save a lot of money with this technology?
Yeah, absolutely. I mean, like anything, it's got a pencil, right? And that's the biggest challenge I think device developers have when they're trying to get physicians or healthcare providers to adopt their technology is what's it going to cost? Is it going to save me money? And if they can demonstrate that, that's going to go a long, long way. So you see a lot of medical device developers showing that their procedures, again, if you have lower complications, that's lower cost because you're out of the hospital faster. Those hospital beds are not cheap to keep someone in it. They're not cheap to staff. If you can offer more preventative outcomes and to avoid a more catastrophic health condition down the road, that's saving costs too. If you can keep your doctors and nurses from burning out and having that kind of turnover and paying the kinds of rates that travel nurses charge, that's a big win as well. So cost is always part of it. This is America. Healthcare is a business, and engineers are always thinking about that from the very get go. We even talk about tariffs and something like copper. We've got potentially new copper tariffs on the way. And it turns out, I set out to say, I wonder just which ways copper is used in medical devices. And of course, anything with a circuit board, right? Anything with a battery, with a motor, with wires, connectors, cables. Turns out that's a lot of medical devices, and it's in it. So you've got a lot of people thinking about supply chain, thinking about, okay, how do we handle some of these costs and maybe, try to reduce the material that they're using. It's a little bit new piece of the puzzle, and maybe it's a few cents per device, but that adds up at scale.
Yeah, yeah, yeah. Jim, it's all this technology. The rate at which it's moving, of course, is it's difficult, I think, for lay people to even keep tabs in this, and it surprises us all, even within the engineering community. Project your mind forward 25, 30, 40 years, essentially. What do you think we're going to see in the future? Basically, will this be completely automated? Will they be AI enabled robotics, and will you basically strap yourself into a chamber like science fiction, essentially, and untouched by human hand, sort of emerge with a complex surgical procedure?
Yeah, it's hard to imagine what exactly will be possible in 20 to 30 years. I just look back 20 years ago to how far we've come now, where we do have robots inside. I think we'll still need to have humans in the loop, right? You still want people making those kinds of decisions because it's so life and death. There's not a lot of do overs if you get something wrong. But if we can use technology I think the big trends that are going to be continuing is miniaturization. You talked about smaller devices, smaller systems able to reach in less obtrusively, go farther in, even to the point where we have microscopic devices that are baked in nuclear reactors to be delivered directly to the site of a tumor to kill that tumor. That's happening today. To imagine what's possible in 20 years, what I'm really hopeful for is that we are going to, again, I'm a huge enthusiast for nitinol. What I can't wait for to happen is for us to really get our hands on how you can take advantage of that temperature transformation. Because right now, if you wanted to let's say, resize a shunt within a patient by heating it to achieve that shape memory, well, you're putting a lot of heat inside of a patient, and it turns out the body does not like that. So there are startups right now, there are very smart companies working on how can you apply the heat, or how can you apply this energy within a patient to achieve a different, almost a resizing of a medical device. Imagine a stent or some sort of implant that you have to put in for a pediatric implant or pediatric condition, and then you have to adjust it as their body grows and they get older and older. There's some patients that when they get pediatric implants, they have to go in and get them replaced and replaced. If you could resize them with a minimally invasive procedure, if you could resize them almost from outside the body with some sort of magnetic or electromagnetic burst, what an incredible thing that would be.
And Jim, for listeners who are interested in learning more about nitinol in particular and a lot of other technology, I see that you've got a feature article on that on your website. Where can listeners go to learn more about this and other medical technologies?
Yeah, for those who are as excited about nitinol as I am, I would send you to, and I'll give you a short link for a website at medicaldesignandoutsourcing.com. We have a nitinol resource page, and the URL for that is wtwh.me/nitinol. That's going to take you to webinars featuring medical device engineers who are working with nitinol. That's going to take you to our new special report on nitinol. We take you all the way from the journey of where it's melted and all the way through manufacturing, finishing into a human patient. We talk with major med techs and groundbreaking startups that are doing incredible things with nitinol. We've also got an email dedicated to nitinol advances in medicine. And I'm always covering, even to the point where sometimes I say, okay, maybe people are getting kind of tired of nitinol. I'm going to try to cover something else. I get into a device, I get into the FDA documents, I get into the instructions for use. Sure enough, there's nitinol in there. So even when I try to get away from nitinol, it's everywhere. And I'm happy to cover it because it is such an exciting time with this material.
It is an exciting time. Jim Hammerand, Medical Design and Outsourcing. Thanks for joining me on the podcast.
Jim, thanks so much for having me.
That's it for today's Industry Insights and Trends podcast, brought to you by engineering.com. If you like this program and want to keep pace with the latest innovations in engineering, subscribe to our newsletters such as Design Weekly, 3D Printing, Aerospace and Defense, Digital Transformation, Simulation, or a weekly roundup at engineering.com/subscribe. For our deeper engineering series, visit engineering.com TV for exclusive shows like Designing the Future, Manufacturing the Future, and the Engineering Roundtable, found exclusively on engineering.com TV. Thanks for tuning in.